Electric current. Moving charges and electric currents. Electrostatics deals with charges at rest. Now we begin to focus on electric currents, that is, charges in motion. Here we restrict ourselves largely to the study within the framework of classical physics of static currents, of conduction electrons moving through metallic conductors such as copper wires. Although an electric current is a strain of moving charges, not all moving charges constitute an electric current. There must be a net flow of charge through that surface. Two examples clarify our meaning. 1. The free electrons, conduction electrons, in an isolated length of copper wire are in random motion at speeds of the order of 10 to the 6 meters per second. If you pass a hypothetical plane through such a wire, conduction electrons passing through it in both directions at the rate of many billions per second. Hence, there's no net transport of charge, and there's no current through the wire. However, if you connect the ends of the wire to a battery, you slightly bias the flow in one direction, with the result that there now is a net transport of charge and thus an electric current through the wire. 2. The flow of water through a garden hose represents the directed flow of a positive charge, the proton in the water molecules, at rate of perhaps several million coulombs per second. There's no net transport of charge, however, because there's a parallel flow of negative charge, the electrons in the water molecules, of exactly the same amount moving exactly the same direction. Electric current. It is copper wire, no electric field. There's equal potential body. There's no current. But if we connect a battery, electromotive force devices, to this copper wire, we will see there will be current flow from positive to the negative pole of the battery. Then we have electric field in the copper wire, and this copper wire are not equal potential. You have a current inside. Now we define the current. I is dq dt, as definition. So from this one we move dt over here. So dq equal to I dt. We do the integration, we get it q. What this mean? This means it's time 0 to t. How many charge passing the cross section of this wire? A prime, BB prime, C prime, they're all the same. Q. The metric system unit for current is ampere. At 1 ampere equals 1 coulomb per second. You look at the current, it has direction, but it's not a fact. It has scalar, because vector should obey some rule. If you don't obey that rule, you are not belong to the vector. Current is one of them. A current arrow is drawn in a direction in which positive charge carriers would move, even if the actual charge carriers are negative and move in the opposite direction. Under steady state condition, no stuck somewhere, sigma I equals 0 at any jump point. You have 3 connections called a junk. At any jump, sigma I equals 0. What does this mean? This means the current flow in the junk equal to the current flow out of the junk. The current flow in the junk equals positive. The current leave the junk equals the negative. Current density J. Sometimes we are interested in the current I in a particular conductor. At other times, we take a localized view and study the flow of charges at a particular point with the conductor. A positive charge carrier at a given point will flow in the direction of the electric field E at that point. To describe this flow, we can use the current density J. This vector quantity has the same vector direction as the electric field on a surface and has magnitude J equal to the current per unit area through an element of that surface. Now we look at this I. The streamline presents the current density in the flow of a charge through a constructed conductor. We can write the amount of current through the elements as J dot dA. J is the current per unit area. dA is the area, so J dot dA is the current. Where dA is a vector, is the area vector of that element, perpendicular to that element. The total current through the surface is then I equals J dot dA integration. Okay. I is not just scalar. J is a vector. Okay. If the current is uniform across the surface and parallel to dA, the J is also uniform and parallel to dA. Then above equation becomes J dot dA equal to J dA, because they're parallel. And into the integration, okay, J is constant, take it out. Integration, differentiation, you get A. So this is a uniform situation. Okay? Okay. So J could I over A. This is magnitude. Where A is the total area of the surface. From above equation, we see that the metric system unit of current density is ampere over square meter. Ampere over square meter. Drift speed, Vd. The conducting electrons in a copper conductor is random direct velocity, about 10 to the 6 meter per second. Huge, huge. It's random. The average velocity is 0. Okay, and you have a drift average speed. Okay, 10 to the minus 7. It's much smaller than this one you see. Okay, and this drift speed is responsible for the current. We can prove it later. The current density J equal to NeV drift. Okay, N is the charge number per unit volume. E is electric charge for electron. Now, let's find the charge density J. Now, suppose we have a current through a wire with cross section A. Okay, and then we look at this section L, where the charge carriers come from. Because from outside. Okay, with velocity Vt, the length L, so it takes time. Okay, the time is L over Vd. This time, okay, you go this far. And how many charges you have? The Q. This is the Q. Actually, all these ones are passing through across the Q. This Q is the charge density multiplied by the volume. Volume is cross area A, length A, the volume. So this is a total charge carrier. Each carrier with charge E. This is a Q. Okay, number times charge, the total Q. How much time? Now, in this time, L over Vc. Within this time, you have this charge flow in, right? So I is Q over delta T. You put it inside. Q is NALE. Delta T is L over V. So we find I. Well, cancel out the L, we get MC. And J is I over A per unit area current. Okay, and then equal to NEV. That's the formula we have to see. So J is related to directed speed. Okay, if the current is positive, then they have the same direction. If the current is negative, they have opposite direction. Okay. Sample. The current density of a cylindrical wire of radius a big R, 2.0 millimeter, is uniform across a cross section of the wire, and is J equal to 2.0 times 10 to the 5th ampere per square meter. This is uniform. Question: what is the current? So the outer portion of the wire between radial distance half R and R. Now, this is half R, this is R. So this outside section, I want to find the current. Now, it's very simple. First, we find the area. This area should be pi R squared minus pi half R squared. This is the area. Okay? You have area, you have J. I equal to J8. You know J. Okay? We have to write it in ampere. Okay, it's ampere. Put this one inside. Okay, we get current 1.98. Very easy. Question B. Suppose instead that the current density so a cross section varies with radial distance R at J equal to alpha R squared. The bigger the R, the larger the J. With alpha equals 3.0 times 10 to the 11 ampere per square meter, and R is in meters. What now is the current, so the same outer portion of the wire? We define the current, so this ring outer wire. But this time, the J are not uniform. Okay? So what we do, we still use this word J dot dA. The J is not uniform. So what the J, we look at J is alpha R squared. Same R, same J. So we check out a ring. The thickness ring is dr, very thick. The radius is R. Okay, you look this one. In this ring, because they have the same R, so the J is the same. So we can use J dot dA with J times dA. Okay? The J is alpha R squared. They are the same. And the area dA is 2 pi R multiplied by dr. So that's what they put it. So they are the same direction. Okay? So we put the J dA. This is this one. And the dA we take this direction. Okay? Yeah. And then we put them inside and do the integration. The integration R is from half big R to big R. Then we'll get the answer. Okay? This is integration is R for the force. Okay? Okay. And finally we get this one. We put R in, you get a number. Okay? This is pi alpha 3 times 10 to 11. R, you have to use the meter as a unit. So this is 0.002 meter. We get I. Sample. What is the directed speed of the conduction electrons in a copper wire with radius R 900 micrometer when it has a uniform current I 17 milliampere? Assume that each copper atom contributes one conduction electron to the current, and the current density is uniform across the wire's cross-section. So we'll find the speed, okay, so speed, drifting. We have to find the current density, J, because J equal to NEV directed speed. How to find N? This is the carrier number per unit volume. This is for cubic meter. And then we see is total number divided by the volume. Total number equal to the mass of the copper divided by the molecular weight of the copper. This is a mole percentage. Each mole you have Avogadro number n. So that's the n. Is n. Volume is V. Okay? Yeah. So then what we do, we move this m over v and a over v. The mass m over v, what is it? This is mass, the volume, so this is density. Density of copper. And this one is Avogadro number. This one is the molecular weight of copper. You can check on the table, right? So finally, put this one inside. This can check everything. You get this one. All right. We know n. We know j. J equal to I over A. This is A is okay. A. So this is J. J equal to N E V. So we find what this is. V drift equal to I over N E A. Okay. This A is area. This is pi r squared. We have R. We have to put the R as a meter as a unit. Okay, so we put number inside. This I is ampere as a unit minus 3. Okay, this is the one we calculate. Okay, and then we find this is a charge of electricity, and this pi r, this R should put in meter as a unit. Okay. So finally, we get the drift speed. Look at the drift speed. It's 1.8 millimeter per hour. 1 hour or the less than 2 millimeter. The speed is slower than a sluggish snail. You will never expect that one. You will think the speed is so fast because when they turn the switch on, the light bulb shining. Okay, it's very fast, but actually it's very slow. What is fast? Actually, the fast is the propagation of an electromagnetic wave with speed c.